This conference
Yes,
will
I
now
am
be
sharing the
recorded.
screen. I'm sharing the screen. Can anybody see it?
Sam, you have the superpowers. I still only see Richard right now. Oh, I
Yes,
see
sir.
it.
I can see
Sorry.
it.
Can you guys see my screen?
Yes, we can see
Richard, I can see it.
Okay.
Yep.
So first of all, thank you very much for having me here. Thank you for the Ashrae chair, and thank you for Alina and Derek to invite me to join this meeting. I have to be honest to you, I'm super nervous because I have to remove a lot of information, especially the commercial one, from my presentation. So little bit crack here and there, but hopefully we'll get through smoothly. My name is Richard. I'm working for Swigon North America. I'm a regional sales manager looking after the West Territory. At the same time, I'm the application engineering. So I'm working very closely with a consulting engineer. I used to be a consulting engineer too. So today's presentation, I try to differentiate myself from other ERV manufacturers. I'm going to challenge you a lot in the schedule spec. What are you going to schedule? What are you going to spec? What are you going to get? What are you not going to get in this presentation? So feel free to interrupt me if you have any question, if you have a different opinion. I'd be very happy to get into the conversation with you guys. So here's today's agenda. First of all, I'm going to have some overview of a high performance building code, not necessarily for Alaska, but the high performance building I witnessed in the territory. I want to summarize some common components in those high performance building code, and then use that to review what the high efficiency or high performance means to the consulting engineer and how you're going to specify the ERV with high performance. And secondly, we are going to go through a couple of factors that are going to affect the airflow, including the filter and how that are going to affect the performance. And at the same time, I'm going to have a deep dive into the airflow measurement station. I personally strongly recommend for the cold weather. The reason I spend so much time on the airflow, we are going to specify because I personally think it's a great idea to bring in the fresh air into the building, but same time it's very expensive, especially in the cold weather. If you do not have the airflow you specify to bring in the building, you're going to have a lot of other effect to fix it. And the last couple of topic I want to cover is pretty common. The first one is the frost control. That's a common topic. You guys probably already talked about that topic thousands of times. But I just want to share some, the new way to do the frost control and the frost prevention. And the last two are the capacity control. On the one hand, in the cold climate, you probably do not have much shoulder time, but how do you take advantage of the cold air in that kind of situation? That basically related to the capacity control. And the last one, pretty much related to my personal background, is probably not related to the cold weather. But if we have time, we're going to talk about it, talk through it. But if we don't have time, I will just completely omit it. So first of all, I want to show you this climate zone, not only including the United States, but also the Canada. I'm based in Toronto, Canada. I'm pretty much sure we are in the same climate zone, 7 and 8. If I want to give a summary of this climate zone 7 and 8, I would say cold, super cold. So how the high performance building codes looks like. The first one I want to share with everybody is passive house requirement. Passive house requirement is pretty popular in the cold weather. There are a couple requirements. The first one, obviously, you see every day, in your schedule, which is energy recovery efficiency. They recommend 75% and plus. I know it's a little bit surprised, seems to be low, but that's what they're asking for. But on top of that, they basically emphasize another three factor that probably completely missed from your ERV schedule. The first one is the casing leakage. That is basically to us is the case external leakage. The other one is the internal leakage. For the wheel type of ERV, basically that's a wheel cross contamination or the EATR, exhaust air transfer ratio. They're asking for the internal leakage to be 3% or less. The last one is the total unit power consumption to be 0.76 watts per CFM or lower. And when we talk about the passive house, I just want to let you know, passive house, there are two different entities. The one original from German called PHI. They are using PHPP design software and energy modeling. It's completely different entity from the FIAS, which is using the Woofy energy modeler. Just to let you know, they for the passive house United States, from time to time they might borrow those concepts, but in most cases is depending on the energy modeler's choice. Sometimes they're using the PHI certification, sometimes use their own. But the bottom line is they always specify the watts per CFM because that is the power consumption they're going to be consumed by the ERV when they bring the outside air into the building. The next one I want to share with everybody is called the NEA, Northwest Energy Efficiency Alliance, which covers the territory in the West Coast, including Washington, Oregon, but also the Idaho and Montana. In their requirement, you will see they're asking for significantly higher sensible efficiency to be 82% or higher. But at the same time, they also borrow the concept from the PHI. You can choose either way. But on the other hand, on top of the efficiency, energy effective alone, they add a whole lot more criteria to define the very high efficiency HRV or ERVs, including the low specific fan power. It's actually more stringent than the passive house. It's 0.71 than 0.76. They also included the control capacity, economizer mode, which is a capacity control I'm going to cover down the road. They also cover the deforce control. And obviously, they have a definition on the low internal leakage to be 3% or lower. They also cover the casing insulation and outside air filtration as well. The next one is the C46.7 high performance DOI system requirement. From personal point of view, as an epic engineer, I would say that's probably the most difficult local energy code to meet. They actually have only two requirements. One is 80% sensible effectiveness of the DOI system. But it's pretty easy to meet 80%. But on the other hand, when you look into the another requirement, it's a super challenge actually. It's called total combined fan power to be less than 0.5 watts per CFM. It gives a lot of challenge to the energy ERV design and the selection. The reason I'm going to go through all those high performance building code, the reason being is when you're doing the ERV schedule and specification, you probably don't want to exclusively focusing on the high heat exchanger efficiency alone. Basically, that's a sensible efficiency. Instead, you probably found the balance between the energy recovery and the pressure drop or the power consumption. And the reason I'm saying that is because the effective heat exchanger can be increased by tightening up the gap of the heat exchanger, but that always came at the cost. That the cost is actually the higher pressure drop and consequently lead to the higher fan consumption. However, on the other hand, you can basically target at the lower pressure drop, consume less fan power, but at the same time, you're going to have a cost in the energy recovery. But the bottom line is you want to have a balance between those two. You don't want to exclusively focus on the one side and ignore the other. Like I always, joke with a consulting engineer whenever I make a presentation. Hey, I'm not here to come over here to tell you I have the highest energy efficiency in the world. I'm here to tell you we want to have a balanced design between the energy efficiency and the power consumption. So how can we define the word schedule specify the ERV with a proper low energy consumption? The one I would probably recommend is SFP, the ventilation unit specific fan power in watts per CFM. So what is going to affect the SFPV? There are two factors. I will go through this formula first. So SPV equals to electrification divided by the airflow. If we do a quick math, you will find out the SPV, SFP actually all about the pressure drop and the fan efficiency. So looking back to this slide, you're looking for, if you want to have a lower SPV, you want to improve the fan efficiency on the one hand. At the same time, you're trying to design your ERV in such a way that you are going to have a lower pressure drop across all the components of the air handling unit, including the fan cabinet, the fan size, and the filter and the heat exchanger. However, when we look into the fan efficiency, I have some bad news to share with everybody. We are not comparing with induction fan or the motor against the EC motor. The reality is the further development can be expected, but every percent of efficiency improvement is very demanding and very costly. So on the one hand, you can see the EC motor is actually 10% more efficient than any induction motor. Is going to lead a significant annual energy saving. But on the other hand, there's some European standards. The one at the bottom is they are proposing for the future the minimum efficiency for the future IE5 that has not been on the street yet, but you can see they are pretty close to the upper limit. That basically verify the conclusion we just draw, that it's very difficult to further improve the efficiency of the fan. So let's look into another factor, that is a total pressure drop. The total pressure drop basically can be divided into the internal and external. I would say, Mr. Engineer, the external pressure drop is pretty much rely on your design. Because the external static pressure is roughly 50% of the pressure drop. That basically means your design of the ductwork is contribute roughly 50% of the SPV value on average. But at the same time, as a consulting engineer, I know there's a limitations. On the one hand, we want to design the bigger ductwork, but in many cases, they can be physically limited by the space available, right? So let's look into how the ERV can do to reduce the internal pressure drop. A couple factors you want to take into consideration and you want to look closely when you evaluate the ERV design from the manufacturers. The first one is the filter. You can basically use the pleat type of filter versus back type filter. But in the general speaking, the back filter has a larger area for the air to go through, and consequently reduce the air velocity and reduce the internal pressure drop. On the other hand, you want to look into the heat exchanger. make sure they are full size and have a lower pressure drop. And the last one, as I always say, is the balanced cabinet size. On the one hand, I know in some application you definitely want to hide the unit into the ceiling space, but bear in mind that is always come with a cost. Whenever you have a super compact or compact design, you basically narrow down the air gap and then significantly increase the air velocity through that component, and consequently may increase the internal pressure and increase the fan power consumption down the road. So you always want to find the balance. Don't push it to the extreme. Find a balance and find out the watts of the CFM that are going to suit your project. So as for this slide, I would say the bottom line is when you design a ERV system or schedule a ERV project, you probably want to evaluate not only one factor, sensible efficiency, latent efficiency. You definitely want to look into the watts per CFM, because that basically means what kind of operating cost you're going to have down the road for the owner. This slide basically trying to cover what kind of a desiccant is better. When I visit my customer, I got a question all the time. Hey, Richard, we heard there's the silica gel and you're offering, molecule C. Which one is better? I managed to find this chart from third party, and I want to present it here for everybody's information and discussion. I would say if we look closely into this chart on the left side, I will probably say when you have application with the relative humidity higher than 40%, silica gel is obviously winner. But on the other hand, if you have an application with the relative humidity lower than 40%, then molecule C probably can be a better choice. So there's no obvious winner or loser. It's up to your application. And so this hopefully will help clarify what kind of a desiccant question you have when you select the material for the ERV. The next couple slides will quickly go through what efficiency means for the energy recover. I basically comparing a high efficiency ERV, let's say 83%, with our average or standard efficiency ERV with a 62%. So let's say we're running the ERV at 5,000 CFM. The conclusion is the high efficiency ERV will save 64,000 BTU in the heating mode, which is what we care most in the cold climate. But at the same time, just for information, this high efficiency rotor or the heat exchanger basically will going to save roughly 8 tons of cooling capacity if there's this kind of requirement. Do we have any question by far? Okay, I will keep going. So, I'm going to give some explanation to recommend the airflow measurement station to the ERV manufacturer and to the cold climate application. Here is a typical control diagram with a fan with integrate airflow measurement station here, BF1 and BF2. At the same time, there are 4 temperature sensors to monitor the temperature just before and after the wheel. I want to do a quick quiz. You feel free to enter the data in the chat box or just create some number in your mind. Say right now you're review the submittal for a project you specify. And in this project, you wanted an ERV to deliver 1000 CFM for supply air and return air. Balanced airflow, the EATR ratio is 0.5. 0.5. So basically 5 CFM overflow. And the OACF is 1.07. Basically, outside air correction factor equals to 1.07. So just imagine, you tell me, either in your mind or feel free to enter in your chat box, when you're doing the review, how much CFM for the supply air you're expecting, and how much air you're expecting you want to confirm and approve for the exhaust fan in this kind of ERV setup. So this is my interpretation. In this kind of setup with this kind of EATR and OACF, the reality is for the supply air, 1000 CFM, but more than 1000 CFM for the exhaust air. Why? So let's do some quick math. So we are trying to deliver 1000 CFM for the supply air and 1000 CFM for the return air. But the reality is, due to those leakage, the exhaust air will leaking 0.5% from the return air over to the supply air. There are 5 CFM. So in order to get 1000 CFM supply air, you only need to withdraw like 995 outside air from through the wheel on this side. But for the exhaust air, because you have a whole lot of air, leaking from the outside air side and the recoup from the purge section etchers, you're going to have more air than 1000 CFM. So the bottom line is, what I'm saying is, when you design the system, when you review the submittal drawing, you should not only look into, when you evaluate the fan curve, you should be looking very carefully what kind of airflow you can get. Because when you have the airflow not delivered as per you specified, you're going to have excessive infiltration or exfiltration. That might not be a big deal for the mild weather, like in the South California, because there's a lot of leakage here or there. They basically open the window to bring the fresh air. But in the cold weather, you probably have a relatively tighter building envelope, and any additional air going in or going out will cause the energy loss. You have to heating a little bit more or heating a little bit less, depending on the airflow you will get. So as a result, we strongly recommend the flow measurement station into your design. So you can help to correct the flow in the ductwork, help to do the better operation, monitoring, and control. And it can be critical for the constant airflow. At the same time, it's probably even more critical when you're doing the variable flow control. On the other hand, do you think you have an airflow management station alone, you are going to do the job? Let's think about this scenario. The density of the air actually going to be affected significantly by the temperature, especially in the cold weather. In the summer you'll probably get 68, but in the winter you might go down to -4. You can see here there's a big swing of the air density. So just imagine you commission your ERV system in the summertime. I think that's probably pretty common in the cold weather conditions. You probably don't want to do the job in the winter time, right? So you think that you perfectly set up the system to deliver 10,000 CFM in and 10,000 CFM out. Perfect, right? And running perfectly in the summertime. But in reality is, when you still draw like 10,000 CFM out in the winter time, due to the different air density, you will withdraw a whole lot more air from the exhaust air side and cause the negative pressure of your building. The whole building is at the negative, potentially cause the excessive and not required infiltration of the cold air into the building. Then you have to spend more energy to heat that cold air up from that infiltration. On the other hand, you might commission your building in the winter time. You withdraw 10,000 CFM from the return air side and supply 10,000 CFM in the supply air side. But the reality is, when you run the system and without any correction, you're actually going to end up with overpressure of the building. So the conclusion is, we basically recommend to not only have the airflow measurement station to help you deliver the air you specify, but at the same time, you want to have a real-time temperature adjustment. So you can basically adjust the airflow based on the temperature. I believe this can be a good recommendation for the cold climate. And next, I'm going to talk about the filter and how the filter is going to affect the ERV performance in two ways. There are 6 features of a good air handling quality design, and the filter bypass leakage is actually one of them. Ashrae basically recommended to have a MERV 13 filter to improve the central air filtration since the pandemic started. But you had to watching these recommendations very closely. It's actually including 2 recommendations. The first recommendation is to recommend to improve the MERV rating probably from 8 all the way to 13. But on the other hand, don't ignore the second part of the recommendation. Actually, basically recommend the highest compatible with the filter rack and the sealed edge of the filter to limit bypass. I always believe no matter how high the MERV rating is, your filter rating is only as good as your filter rack. That is why certain filter seal design has to be reviewed and checked when you're doing the design and the selection of the ERV manufacturer. The reason being is the first impact on the performance will be on the wheel or on the plate type exchanger, because no matter what kind of a heat exchanger you're going to select, they're all going to experience a decrease in their performance when they are getting dirty. But obviously, wheel type has some advantage because when they're rotating, they actually have some self-cleaning mechanics. On the one hand, the air going to this way, but when they turn into the bottom, the air going to the other direction. So they have a certain self-cleaning mechanics. It's also helped to reduce the maintenance. But the bottom line is, your filter is only as good as your filter rack. So make sure when you look into the Ashrae recommendation on the filter, make sure you pay attention to both. The second part of the filter impact on the performance is actually on the airflow. Again, I cannot emphasize how important for the ERV to deliver the airflow specified. Again, going back to this typical flow chart, you can see here we have BP2 and BP1 pressure sensor to continuously monitor the pressure drops through the filters. So what are they for? Let's say if you're not doing anything when the filter kind of getting dirty, you can see here is a typical fan curve. Here, point A showing the operating status of a clean air filter, and point B showing the operation status of a dirty filter. The bottom line is when you have the filter getting dirty, you are losing the airflow. However, you can do something like this one. You can basically speed up the fan and maintain the airflow you specify. But ignorance of this factor will cost you the loss of the airflow. So let's go through some of the submittals of the curves, fan curves. So depending on the fan curve, some of the fan curve is pretty steep. So they may not lose a lot of airflow when the filter getting dirty. In this case, when the fan curve, when the filter getting dirty, they lost probably 10% on the supply air side and 10% on the return side. But this one is a different story because the fan curve is super flat. And if you do not do anything to speed up the fan and then compensate the pressure drop loss, then you're going to, by theory, you're going to lose 50% of the supply air when the filter getting dirty, and roughly 30% for the exhaust fan. Just bear that in mind. If you do not do anything, you're not going to get the airflow you specify. Do you have any question by far regarding to the airflow? Okay, we'll keep going. Coming to the forest control, we basically can break down into the forest control into two parts. The first one is actually very important, and we need to prevent the forest form as much as we can before we jump into the deforest control. So I basically pull out some data from the Ashrae climate design condition for 2021. But obviously, I have a conversation with Phil before this presentation. Looks like Anchorage have probably relatively mild weather condition comparing the rest of Alaska. So just taking Anchorage as an example. So first of all, I would say it's really up to your judgment call. If you're looking in using the data for 99.6%, I would say for Anchorage, this AFB and AAF and Wasilla, you probably will need some kind of a preheater. But however, on the other hand, if you're using the 99% data, then you will have only one location that will potentially need a preheater. But again, as per my conversation with some of the engineers, it's also depending on the application. So he gave me that example, but again, it's a judgment call. He basically said, you know what, if this is a hospital, no matter how high the temperature is, he probably will throw in a preheater anyway. But on the other hand, if this is a public library, even the outside temperature is close to -20, he will not even throw any preheater. So it's more like a judgment call. Yeah. So when we come to the forest control strategy, there are a couple of strategy has been widely used in the industry, but we can discuss the pro and con and how we can do a slightly better job and improve the energy recovery in the forest control design. So the first one, probably the least used one is shut down the unit when the temperature is below certain temperature. And the second one, you basically time the exhaust, you run this for 10 minutes and then shut down for another 60 minutes, another 50 minutes. And then the next one, you basically, instead of monitor the outside air temperature, you basically monitor the exhaust air temperature and set at, like 23 Fahrenheit. The next one is bypass. I would say bypass probably similar to shut down the unit because you basically completely bypass the system and you're not doing any energy recovery at all. The last one is a preheater. It's depending on the weather condition and also your judgment call. I would say -20 may be a good starting point for you to through the preheater. Sometime, no matter how good the default control strategy is, the preheater is almost unavoidable. But one strategy I want to have a little bit more information to share with everybody here. So basically, instead of using all the the other strategies, this strategy can theoretically save roughly 16% more energy when you need that energy most. So in this scenario, you can see there's a pressure sensor BP5 to continuously monitor the pressure drop through the rotor. When the temperature is getting low and frost begin to build up onto the rotor, what they can do is actually can slow down the rotor to do the dehumidification. So basically, will dehumidify return air as it cools. It's also help lower the dew point and optimize the energy and energy transfer. The hardware is obviously required for this to realize this control strategy and default control. So basically, you need the rotor to be able to change the speed. But the bottom line is you want to slow down the rotor as low as possible. The chart over here is actually the series behind this default control strategy. So basically, there are two curves. The one on the top is the sensible curve, and the one on the bottom is the humidity curve. So you can see here, the latent and the sensible energy recovery process actually behave completely differently in the enthalpy wheel. The latent performance is more linear with the rotor speed, while the sensible rotor capacity behave is more like a water control valve, right? So sensible capacity control only occurs in the last few RPMs. So while wider rotor speed range is critical for the temperature control. In order to do the accurate control, you have to have the hardware to be able to slow down the rotor speed all the way to 1 or 2 RPM to be effective. In other words, if you have a third party to do this kind of programming, make sure you want to have the proper hardware and the software that are able to slow down the wheel speed all the way to this range. If they can only slow down the wheel like 8 or 10, 12, the reality is that's not going to do the proper default control at all. Capacity control. I know it's probably not a big topic in the cold climate, but on the other hand, Toronto and Alaska sharing the same climate zone. In Toronto, we still have a shorter time in the spring and in the summer. So just give you an example, I basically borrowed this slide from one of the Ashrae chapter. I believe this is a good demonstration why the capacity control or economizer is critical. Just say the two extreme scenario. You have super low heat recovery efficiency from your ERV. You have outside air temperature happen to be 55, which equal to your cooling set point, and your room temperature is still maintained as 75. If you keep running your ERV, reality is you're going to have supply air temperature at 65 because you're running your ERV. On the other hand, if you have higher efficiency ERV, then reality is the ERV heat up your air to 71, and then you have to spend a lot of mechanical cooling capacity, bring that temperature from 71 Fahrenheit down to 55. So this slide basically want to let you guys know, in certain scenario, especially in the shoulder time, may not happen very often in your territory, but you want to monitor that closely because you don't want to waste the energy while you design this for the energy saving point of purpose, right? So in that scenario, you probably want to eliminate or find a certain way to bypass the heat recovery. There are a couple strategies. One is doing the bypass damper for the capacity control. You can see here they have a bypass damper for the outside air, but you cannot just bypass the outside air. You want to have a balanced airflow, so they have a bypass damper on the return side as well. It's one of the strategy, but obviously you make this design more complicated, and at the same time you squeeze the room for the wheel. Going back to the first topic we talked about, when you consider about high efficiency ERVs, you're definitely trying to do everything you can to lower the pressure drop so you can reduce the fan power consumption in watts per CFM. This kind of design, reality is, when the rotor running at a normal condition or in the majority of the time in the cold climate, is actually significantly increase the pressure drop and consume a whole lot more power, fan power. But for the plate type heat exchanger, obviously the economizer mode, they definitely want to have a bypass damper, but make sure depending on your local Ashrae recommendation, in certain Ashrae chapter, they basically recommend the bypass damper for supply air side, but also for the return air side. You cannot just have one bypass damper on the outside air side. So since we have a little bit of time, I'm going to talk a little bit about the noise control for the ERV, because going back to the 6 design features of a good air handling quality design, acoustic insulation is one of them. So first of all, you want to building the casing a little bit robust and building with the thicker wall casing. The 2-inch double wall casing probably the minimum you want to go. I'm a little bit surprised to see some of the manufacturer cut a corner and recommended 1-inch casing for the indoor application. I believe that's not going to help reduce the noise, especially the radial noise, especially when they have the unit indoor, probably hanging on the head, on the top of your head. You're going to hear the rumbling. And secondly, is actually the fan arrangement. You can see here is a typical fan arrangement for the EC motor. They rigid connect to the air handling casing. And here's another one. But the problem is they basically have nothing to isolate the mechanical vibration from the fan to the air handler. What you can do, you can basically do something internally. Put the neoprene pad or spring below the fan, and then using the flex joint between the bell mouths to break down the mechanical vibration from the fan to the rest of the air handler casing. So what's the benefit by doing so? So if you're not having the internal isolation, then you have no choice but to put an external isolation. The minimum requirement is you need to have a flexible connection on the ductwork, but that's going to cause significantly amount of energy leaking from those acoustic weak points. On the other hand, if you have internal isolators in place, then you can connect the ductwork directly to the unit, and no external vibration isolator is required at all. And you are going to have less noise leakage to the surroundings. Again, come back. It's actually my noise control background, so I probably already jump the gun showing the next two slides. The reality is a 3 dB difference is a 100% increase in the sound energy, but just a 23% in the loudness. I just want everybody have some number in your mind. Do you know how much dB, how much times louder if there's 10 times difference? Just imagine you have two submittal from a tube manufacturer. One is low noise, and the other one is a little bit louder, but they just have a 10 dB difference. The reality is 10 dB difference is actually 10 times louder. So the next one is, you review the submittal from the manufacturer, and you notice there is a 20 dB difference. Just imagine how many times louder between those two. The answer is 20 dB is actually 100 times louder. Yeah, I would say that is my presentation. I have no choice but cut a lot of information from my commercial version. Yeah, I'm giving back to Phil, and let me know if you have any question you want to ask.
Thanks, Richard. This is Sam. Phil's not here, but I just
Sorry.
have one question. You talked about that internal noise isolation in that last slide. Is that is that right after the fan or before the fan?
The reality is you have internal isolator before the fan. Yeah, here before the bell mouse. Yeah. So the airflow coming from the left to the right.
Okay.
Here. Do I answer your question, Sam?
Yeah, you did. If anyone has any questions, please feel free to put it in the chat box.
Hey, Richard, it's Derek McKenzie. Can you hear me?
Oh, no, I cannot. Thank you, Derek.
Hey, I just wanted to add to the conversation when it comes to DOAS systems that in Alaska, even though it's cool out, we get a pretty good sensible heat diversity, solar gain basically. And a lot of engineers tend to design for what would be, that free cooling mode. You touched on it a little bit, but that design
Really?
aspect,
Okay.
yeah, that design aspect is definitely available in DOAS systems, even though we are designing for reduced airflows. That there are demand control ventilation options and systems even available within DOAS type of designs to account for that. So I just wanted to add that to the discussion.
Well, it's good to know. Yeah, I basically added that portion at the last minute. I didn't realize there's potential requirement for the free cooling and the economize mode. I forgot to mention, I basically, let me share my screen again. Yeah. So basically, bypass damper probably is not a great idea. What we can do for the rotary type of heat exchanger, we can basically modulate the wheel speed. So for example, when you have 55 outside air or close to the set point that you are looking for, the DOI system is able to monitor and slow down the wheel speed to all the way to 0 until you reach your set point, and not wasting any energy, but same time, you take advantage of the free cooling. But on the other hand, when you have the rotor in the idle situation, it's probably not great for the rotor performance down the road, because you having all the air going through the one direction all the time. You basically defeat the self-cleaning mechanics. So what we can do is rotate the rotor like 10 RPM per hour, just for the purge purpose or the cleaning purpose. Yeah. Any other questions?
Is there a minimum temperature that you like to see inside for outside air?
I would say this a little bit manufacturer specific. We can handle -40, very high. From my R&D department. Yeah. Any other questions? But again, if you have any further question after this meeting, please feel free to send an email to Derek or Elena, so we can help answer the question from there. Looks like at the least I going through all the slides, I remove all the commercial information. I did not even leave my contact information in the slide, but looks like I'm not going to end up in the jail. So it's a very good news.